Hello. Thank you. Uh, do you hear me actually? Does this? Okay. My name is Arsen Yeghiazaryan. I'm the Deputy Chief AI Officer at Softconstruct. I'll talk today and how to evaluate it, and also will speak about line is going to be the following. So we'll first speak about like quickly why A/B test is important. Then just refresh some statistical foundations, mainly central limit theorem. We'll talk about the problems that the skewed distributions contain for A/B testing. We'll talk about the evaluation methods, the power of the test, and also the variance reduction techniques. We'll wrap up with briefly mentioning the problem of multiple testing, and then we will conclude. So why A/B testing is important? Because so why A/B testing is important is because if you have a hypothesis and you want to test it, whether it works or not. For example, you came up with a new feature and you want to see if it's going to increase the turnover of the business or not. The best thing that humanity has came up with till now is the A/B testing. You basically split your user pool into two groups, toggle the feature for one, and then test if the feature works. Yeah. Okay. Okay. I'll try to be a bit louder. Thank you. 1-1. Okay. I think it's a bit better with this, but I'll try to speak louder. Okay. Another important thing for speaking for A/B testing is the fact that you make the effects more quantifiable and you can report it to the business in a more clear way, and also it allows to roll back the features if you if something is going wrong. Let's briefly touch about the types of metrics that we are going to work with. Is the value metrics and the ratio metrics. Basically, value metrics is the metrics like revenue, turnover, etc., and the ratio metrics is the ratio of two value metrics. For example, the conversion rate or CTR, or for example, in case of online casinos, like what Softconstruct is doing, we have a value metric like the bet count of the users, and also we have the metric like bet amount, overall bet amount of the users, and the metric like bet amount per bet is also ratio metric, an example of ratio metric. So let's actually start with the central limit theorem and what it says, like quickly go through it. Let's actually see it based on these two slides. This one first, and so basically what central limit theorem says, that if you have a distribution which is represented by this gray plot, if you have a distribution and you take samples of size n, then the mean, once you have like many these type of samples and many means, these means are distributed normally. This is basically what the central limit theorem says, and it also says that the variance of that new Gaussian distribution that you get for bigger is the sample size, the more precise estimate of the mean you. Yeah, from here actually let's jump straight to the A/B testing, and because this central limit theorem foundation of A/B testing, what does it say? So present a sample from your population, and as we already learned, the sample means of A and B groups, they are both actually data points from this distribution of means. So if you actually have, again, if you have two groups, A and B, their means are samples from the same Gaussian distribution, which means actually their difference between the means of the group A and group B This is also like a Gaussian distribution, just based on the properties of Gaussian. The difference of two Gaussian is Gaussian, where the mean is the difference of the means and the variance is the sum of the variances. Or in other words, if you actually, oh, I see it's a bit distorted. This is sorry for this. But in any case, we can see that this variable should be distributed as a standard normal. So what A/B test actually does, it takes two groups, A and B, it computes their variances, it computes their means, it computes this entity, and then when it receives a value, let's say 0.3 or minus 0.7, it says if the value is close to zero, then the probability of getting that was reasonable. That means that there is no difference between the groups A and B. While if we get a result like 2 or 2.3, it would mean that this distribution most probably hasn't come from standard normal, which would mean that the initial assumption, the null hypothesis, that the two groups are totally equivalent, there's something wrong with it, and there actually is an effect between the group A and group B. And yeah, I think it's good to illustrate with an example of, let's say, coin toss. You have a coin and you want to check if it's fair or not, and you just have, let's say, you define it in advance. You decide that you are going to have 5 tosses, and based on those 5 tosses, you are going to give a decision if the coin is fair or it's not fair. One way to do it is to decide in advance that if I toss it 5 times and if I get 5 heads or 5 tails, then most probably it's not fair. Even though the probability of getting that, like 5 heads, is 1/32, it's not that bad, like 3%, and 5 heads or 5 tails, it's about like 5 to 6%. So it's not an absurd probability, but if you decide it in advance, if you actually observe that, you declare the coin unfair. And this is the type 1 error this is called the type 1 error, or the false positive error. False positive error means you say that there's actually an effect when the effect wasn't there. Or in this case, we claim that the coin is unfair when it actually was fair. Again, in A/B testing, in some percent of the cases, and the industry standard is 5%, we are going to have this false positive error rate, which is going to say that, which is the fact that we are claiming that there actually is an effect, is a difference between the two groups, when actually the difference wasn't there. And it seems like we can actually control this. We can actually predefine this false positive rate or type 1 error from 5% and decrease it to a smaller value. It seems like, or basically we can, which is equivalent to moving this dashed line to the to further right, but it's not coming for free. Let's understand why. So again, when we have two groups and there's no difference between these two groups, then the mathematics says that the difference between two groups divided by the variance should be distributed as a standard normal, and it should be distributed around the zero, centered around zero. While if there is a difference between the two groups, A and B, then the distribution of the means between A and B should be actually like shifted from zero. In this case, if the effect is positive, it should be shifted to the right. And I already mentioned that about type 1 error, which says that if we take the statistics, like take the means of the two groups, compute the statistics here, then if we get a value which was 5% or less probable to observe in case of the null hypothesis, then we declare that there was no effect. What does this mean? That actually, if there is an effect which is represented by this green line, and if this effect actually is to the left of this dashed line, then we are going to commit a type 2 error, which is the false negative error, which says that there was no effect when actually there was one. And from here, we can see that actually the false positive and false negative errors are interconnected. There's a trade-off between the two. If you want to decrease the type 1 error, which means move the dashed line here, then you are going to increase the shaded area here, which means you are going to increase the type 2 error. I think this is like the basic stuff of the A/B testing. So I'm not going to like dive much deeper here. Just define the last and most important term in the A/B testing, which is the power. So the power is simply 1 minus the type 2 error, which is so the power is represents our ability to detect an effect when the effect is actually there. It's very important because if we injected a feature, edit a feature in which gives actually an effect, we want to detect it. If we don't, if we fail to detect that effect, the whole experiment was a failure. And also from here, it's important to understand that the variance is very important here because if the distribution of the means has a high variance, that means that the power of the test is smaller. Just imagine the dashed line here and the dashed line here. It's obvious that the power for the high variance distributions is much smaller. So one way to actually increase the power of our tests is by making the distributions as narrow as possible. So we're going to talk about the techniques to reduce this variance, but one of the obvious ones, which is evident from this formula, and we also know from central limit theorem, is just by increasing the sample size. If you have a bigger sample, that means your variance is lower, and that means your power is higher. So if you want like good A/B tests, then strive for big sample sizes, which if you can make it as big as possible, then good for you. But like in general, you are limited with the user pool that you have. Now, what's the problem? Like, what is the metrics that you are working with at Softconstruct? For example, is the turnover of the user that the user generates, and the thing is that these metrics are very zero inflated and have very big outliers. What does this mean? That means that like 30 to let's say about 30% of the users, their turnover is very small. Their contribution to the business is very small. And there are like very few people whose contribution is really, really big compared to the rest. The problem with this is that it simply inflates the variance, and we know that high variance is bad for A/B testing. And also, another thing with this type of metrics is that when you randomly split the user pool into two groups, A and B, just because some outliers fell into one group and not the other, this is going to distort the picture and going to make the effect harder to detect. Okay, let's talk about the tests, like very briefly, how we actually test the effects. I already mentioned about this. You basically compute this metric and see if this value is close to 0, then you say that actually there is no effect and the two groups are identical. And if this if this value is too far off from 0, then you say that actually you found something and there is an effect and there is a difference between the two groups. This is called the parametric way of detecting an effect. There's also a non-parametric way of detecting an effect. I'll show one method of that is the permutation test. So what it does, it actually just so the code is actually more descriptive than my words. Basically, it says that you have two groups. You take the difference between the means of the two groups, and this is going to be your observed difference. But at the same time, if these two groups are coming from the same distribution, you can recombine these two groups back and then do a new split randomly, and again compute the difference of the means. And if you do this many times, then what you observed shouldn't be like much different than the distribution of the diffs that you get. And if it's not so, then definitely your original groups had a difference. They were not from the same distribution. Okay, so now that we know what power is, what type 1, type 2 errors are, etc., now let's talk about the A/B test design, which is the most important thing, like how you design, how you prepare to run an A/B test. The AA testing is the phase where you are designing designing your test. So you actually have split the data, and you split your user group and into 2 groups, and you assume that there's no effect because you haven't injected yet any effect, you haven't toggled any feature, so these 2 groups are equivalent. And I actually saw that there's a 5-minute sign, but I'm not going to finish in 5 minutes, so at least. So we assume there's no difference between the 2 groups, and we actually need to check that there is no difference between 2 groups. Again, you can look at the code. Basically, what the code does, it takes your data, randomly splits into 2 groups many times, and calculates the statistics between the 2 groups. And what you should get is a uniform distribution for the p-values, and also you should get that you receive the type 1 error at around the rate that you have designed, which is about 5%. That's the industry standard. And if you don't get this, then you need to actually go back and check your design. Because if you, for example, get your type 1 error rate at 0.2 instead of 0.05 or 0.01, even lower, that means either you are committing your type 1 errors, false positive errors, either too frequently, or you have designed your test too strictly, which means you are going to have, detect the effect in less frequently. Actually, let's keep this slide. So we talked about the type 1 error and just checking if it's controlled. And then let's talk about the power of the test. So now you need to understand what power your test has. The good thing is that you can actually, again, simulate it and understand where is your power, like what is the power of your test. Again, you can see here in the code snippet. Again, sorry for this. On my laptop, it was looking much nicer. So you basically take your data again, split randomly into 2 groups, inject an effect artificially. Here it's just multiplying by 1 plus effect. You can come up with more sophisticated ways of injecting effects, but this is good enough. And just do it like many times and seeing like how many splits have you actually detected an effect. And based on that, you actually draw these power curves, and it shows you like at which size and at which effect size, like at which group size and which effect size, what power do you have. The industry standard, again, is to strive at least for 80% power, so 5% type 1 error rate and 80% power. And if you don't have 80% power, yes, you can run the test, but still that would mean if your power is 50%, that would mean that if your feature actually works, if you actually have achieved an effect, you are only going to detect it in 50% of the cases, which actually is quite low. But well, we already mentioned that by increasing the sample size, you can actually increase the power of your test. But how you can actually increase the sample size is not that easy. If you have, let's say, 100,000 users, then you can't go bigger than 100,000. But the thing is that depending on the business and depending on the metric that you are evaluating, sometimes you are only interested in the users that actually do something, actually perform an action. In that case, by just waiting longer, by running the test for not 1 week, but let's say 2 weeks or 3 weeks, you get more users actually stepping into the pool, which effectively increases the size of the sample. But let me actually bring an example of our Softconstruct's one of the A/B tests at Softconstruct. Basically, we have a recommender system, and we want to check if the recommender system actually boosts the activity in the platform or not. So we take all the users which were active in the last 3 months, and and try to estimate and try to estimate if this recommender system has an effect on them or not. So in this case, we let's say end up with a pool of 100,000 users, and this is the number of users that we work with. We can't neither reduce it nor increase it. This is what we're working with. The good news here is that even in this case, if you actually keep the test for longer, you still can get a power boost. This is why. Actually, with time, the mean of your distribution, it increases linearly with time, while the variance of the or standard deviation of the distribution, actually it increases with the as the square root of time. So these are like asymptotic estimates. So which means that this value, which is called like variance to mean ratio or something like that. I don't remember. It has actually a name. It actually goes down as 1 over square root of t. That means actually if you keep it longer, the power increases. And the good thing again here is that you can simulate this. You can take your data before the test starts and do a simulation for 2 weeks, do a simulation for 3 weeks, and see, of course, which one at which sample size you have the power that you actually need. Of course, the longer you keep the test, it brings its own negatives. Like if it's something harmful, then actually you lose time. So basically, the trade-off here is higher power against a slower iteration time. Okay, so now we know how to design also the A/B tests. Now let's go back to the original question of variance reduction, which is so important for increasing the power. How to reduce the variance? One quick way, like quick thing that immediately comes to mind is outlier, like handling the outliers. Because if you drop the outliers here, then for example here, if we drop the outliers, the variance goes down significantly. And but there's a correct way and wrong way to do it. And the correct way is whatever you do it in the test, in the pre-test period, in your design period. So basically, you decide that you are going to drop the outliers by 99.9 percentile, but you do it only in the pre-test period. And in the test period, you just keep the users that you've already made the design for. And also another technique is the so-called Windsorization, where you take the pre-test period data, you take the, again, 99.9 percentile value, and you set it as a hard threshold. So for anyone who actually is exceeding this threshold, you just put this hard threshold, saying that actually any value above this is actually more distortion and noise rather than, or anomaly rather than representation of my underlying distribution. And also you do dual reporting. This is also important, which will also make sense for the business. You just say that this is my, let's say, estimation of the effect with and without the outliers. And sometimes this can be insightful. Another way, like to reduce the variance, is the stratification. So let's quickly go through it as well. Basically, you can do stratification based on different criteria. For example, the geo-region is the one thing that's easy to do, or mobile versus desktop application strata, etc. But what we can try is, if let's say we are testing the effect on turnover, we can take the turnovers of all the users, split it by percentiles, and like for example here, I take 10, 25, 50, whatever. So all the percentiles, split my scale, and then do a random splitting within each stratum. This actually helps you to end up with a better distribution, with more equal distribution between group A and B. Okay, let's actually not stay here for any longer. Just one important point about this is that however you do this, it's very important to keep your split and your test methods consistent with each other. If you do like stratified split, then also you need to do you need to change your permutation test and t-test accordingly. You need to use the stratified version of those. Actually, let's jump to the one more thing. This is we are getting close to the end. Basically, this is one thing that we were trying to do at Softconstruct, and it's a very interesting thing to try, and it's the following. So let's imagine we're trying to estimate the turnover per user, like average turnover per user. We can decompose the original metrics into three factors, which is the active days per user, number of bets per active day, and then bet amount per bet. This is like mathematically correct. We just decompose the metrics into three factors. And the thing is that actually each of these factors has lower variance, much lower variance than the original metrics. Because active days, if we run the test for 3 weeks, that means it's numbers from 1 to 21. There's no outliers here, like pretty narrow distribution. This metric as well, there's most probably wouldn't be users who are doing 15,000 bet per day, so the outliers are not that extreme here. And this also is pretty contained compared to these metrics. And if we actually make a test on each of these and then detect an effect, let's say we detect 3% effect here and 5% effect here, it seems like we can recombine this, and like 3 and 5, it's 8% on the overall metrics, and seems like we actually found a hack. We can actually estimate the smaller variance metrics and then recombine it back. But the thing is that it's not actually true. It's not working like this. The reason is that it's because the mean value of the product doesn't equal the product of the means. Just to give also unless there is no correlation between the M1, M2, and M3. Just to give you an overall, like an intuition why it's so, let's imagine that we decompose the turnover into two factors. One is the active, like number of active users, and the second is the turnover per active user. So if actually we found a feature that somehow activates the dormant users who contribute almost zero turnover, like their active days becomes from 0 to 1, this would mean that we actually have found an effect on the first factor, let's say 5%, while the turnover per user hasn't changed much. It doesn't mean that just because 5% more users have started to play, and these are like the very low players, it doesn't mean that my all turnover has actually increased by 5%. This seems nice at the beginning, but actually this is not the correct way to do the that's in this case turnover evaluation. It's the important thing here, like the way you should proceed, still keep the turnover, the original metrics, as the gatekeeper metric. You either detect an effect there or you do not, but this is the decision maker. So this is the final decider. But you can keep actually the other three, and they are very useful for interpretation, especially for the business. When you say that you have detected an effect like of 5%, and it comes just from the bet amount per bet, so number of bets remained the same, but let's say the people started to play more, then it's also like a very insightful, a very interesting insight for the business. Okay, I think we can wrap up. So basically what we did, we just spoke about A/B design, how it's how we should do it correctly. We spoke about the variance reduction techniques, also like about the stratification and decomposition. And also like made a small refresher about central limit theorem, about the relationship of variance with the power of the test, etc. And we are doing this in Softconstruct for already like half a year. We are not like experienced professional in all this because we are learning. A/B test is really like a very it's a very tricky thing, and so if any one of you is actually doing A/B tests at your companies, we'll be happy to connect, to discuss. And actually we also have open positions at Softconstruct. So if you're interested to join our team, we also have a booth upstairs. Please. Thank you. That was it.
We have time for one or two quick questions, and then later on you can, of course, catch up with Arsen.
Thank you for presentation. The question is the following. How many data in each group at least we should have to consider the test reliable? I mean, for example, if in the first group we have 20 data points and in the second group 15 points, can we consider the test reliable?
One important thing is the group should be big enough in order for the central limit theorem to work. And in case of it's not working that well. Also, we are working with user pools of at least 10,000 and in general, like on average 50 to 100. And that's why these questions, like we don't even ask ourselves what would happen if there were 50 users. But yeah, it should be the central limit theorem should work. For that, you should have at least several hundred sample size. And you can always do these power simulations as well, and that can give you an understanding of where are your design.
Okay, thank you.
Thanks for the interesting talk. I would like to ask, which metrics do you compare? Is it only mean and proportion, or do you also compare on stuff like median, percentile, stuff like that?
Actually, it's a good question. So we are comparing mainly the means, and what this permit. By the way, so I should have actually mentioned that. One advantage of this permutation test over the t-test, with t-test you can just compare the means. With the permutation test, yes, you can compare the percentiles. You're doing A/B tests at Pixar, right? I think.
Yes.
Yeah, we definitely should discuss this later. But yeah, we can. This allows to compare the medians, the 90th percentile or something, which also most probably can be an interesting metric.